I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
The simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that,
and my voice gets really low, although somehow I'm still funny. It's scientific!
The ideal gas law, PV equals nRT, has several numbers in it. P is for pressure. Pressure can be measured in any units as long as your constant agrees with it. Pressure can be measured in atmospheres, kilopascals, torr, millimeters of mercury, as well as several others. Pascals or kilopascals is the SI unit. V is volume and can be measured in anything but usually is measured in liters. N is the number of moles and is obviously measured in moles. R is the universal gas constant, a constant that units have to agree with the other numbers. And T is temperature, and it must be measured in Kelvin. The value of R that we commonly use is 0.0821 liter atmospheres per mole Kelvin. That means the volume's in liters, the pressure's in atmospheres, moles is obviously in moles, and temperature's in Kelvin. That is given on your equation sheet. We cannot do mathematical problems when we see a problem where the conditions of the gas are not changing. They're just asking about the gas at one condition. In this problem, we see that N equals 2.58, volume equals, pressure equals 1.03 atmospheres, temperature is 26.2 degrees Celsius. However, we have to change that to Kelvin. So in Kelvin, that equals 299.4 Kelvin. You just add 273.15 to the temperature in Celsius. We can now do this problem. I always like rearranging these problems so I can solve what I'm looking for. So V equals nRT over P by dividing both sides by P. I now plug in my numbers. Knowing that my pressure is in atmospheres, I can use this R and I come up with an answer. And I get 61.6 liters. 3 significant figures. The first thing I always do is write down the numbers that I'm given in the problem. I have the moles, I have the volume, I have temperature. Room temperature, if it doesn't give you a temperature, is always defined as 25 degrees Celsius. That's just a convention we use. I'm going to rearrange the equation for pressure. I'm going to plug my numbers in, remembering that I have to change Celsius into Kelvin by adding 273, and I come up with an answer, here needing 2 significant figures. I come up with 252.6 degrees or atmospheres, so that's 250 atmospheres to 2 significant figures. I use 2 significant figures because my volume has 2 significant figures. Temperature is a tough one. You can see it has 3 once I turn it to Kelvin. In this problem it asks for density. I know that the number of moles equals the grams divided by the molar mass. I can plug that in, substituting in for N, and then I know that density is equal to grams over liters. So I can rearrange this equation to get mass over volume, and I come up with an equation for density. The pressure times the molar mass divided by RT, the constant in temperature, equals my density. Again, I can look at the numbers I have in this problem, and I can see right away I need to do 2 conversions. I need to convert pressure to atmospheres and temperature into Kelvin. To convert the pressure, I start with what I know, and I know that 760 millimeters of mercury is equal to 1 atmosphere. And so when I do the math, I get 0.986 atmospheres. The temperature is easier. All we have to do is add 273.15 to the Celsius temperature. Once again now, we can plug our numbers in. Since it's hydrogen gas, we know the molar mass is 2.0. We use the same R because we've converted our pressure into atmospheres and our temperature into Kelvin. And I come up with an answer of 8.21 times 10 to the negative second grams per liter. I want this one to be 3 significant figures because of the pressure and the mass. And again, we could rearrange this equation to solve for other things. To rearrange for grams, it's similar. We'd have PV times the molar mass over RT. Again, we need to convert our temperature into Kelvin, as always. And again, we know the molar mass because its hydrogen is 2. We can plug these things in. I can move this to 299K because I only need 3 significant figures. And I come up with 1.28 grams of hydrogen.